This chapter is on electromagnetism or electromagnetic fields. It's the combination of many centuries worth of work in physics that now has the marriage of electricity and magnetism together. James Clerk Maxwell, in his equations, Maxwell's equations, laid the foundation for understanding how we can propagate the properties of and manipulate the different facets, components of everything that is found in radiation. It turns out that there are 7 forms of radiation known to exist in the universe. We'll get to all of those soon in this chapter. So here's a picture, an actual photograph taken by multiple telescopes with the images superimposed, because telescopes can take pictures in different wavelengths, if you will. The human eye, for example, we're only sensitive to about 400 nanometers to 700 nanometers. That part of light is what we call visible light, and that's the only parts that we can see. But there are other animals, of course, that can see in different parts of the spectrum, and telescopes can take pictures in all parts of the spectrum. This is a phenomenal picture of the entire universe, really. That's going to show the curvature of an egg, so to speak, because the universe it closes on itself. All forms of known frequencies, from gamma rays to X-rays, ultraviolet, visible light, infrared, microwaves, and radio waves. These are the 7 forms of radiation known to exist in the universe. And this is a picture of the universe of all of them, all 7 forms of radiation taken at the same time. Pretty cool, actually. Let's take a look at what's in this chapter. So these are Maxwell's equations in a different form. And more of a flowchart type representation. These are the equations from James Clerk Maxwell, and that has to deal with the interrelationship between electric charges, electric fields, magnets, and magnetic fields, and currents as well, and the speed of light, and how they're all intrinsically related. And this is the flowchart representation of Maxwell's equation. This is, you're looking at the representation of all of electromagnetism here, and this is a graphical representation of all 4 of Maxwell's equations, and so the reader can spend the time to take a look at these in great detail. So there are many different representations. This is the importance of Maxwell's equations to the field of electromagnetism. I've taken the time to give the reader different representations of the same thing, so hopefully one of them will make sense, or maybe more than one will make sense. So there's this thing called the electromagnetic spectrum, which shows all 7 forms of radiation that I mentioned. And this chapter talks about the properties of each type of radiation, how our sun and every star, our sun is just but one star out of many other stars. There are some estimated 400 billion stars just in our Milky Way galaxy alone. And our galaxy is by no means the only galaxy. By some estimates, there are about 125 billion other galaxies, each with trillions, hundreds of trillions, maybe trillions of stars. So with the sheer numbers involved, there are countless stars that exist. Some 100 million, billion, trillion stars scattered throughout the universe, and they all produce the same thing. 7 forms of radiation, all the components of the electromagnetic spectrum. So this chapter talks in some great detail about the different facets of the electromagnetic spectrum, everything from gamma rays to radio waves, and how we can artificially recreate each type of natural radiation and what kind of uses we've put to the different kinds of radiation. For example, the infrared used in the military for night vision. Radio waves are used for communication. X-rays are used for security measures and for taking X-rays of broken bones, for example. So we found a way to mimic natural sunlight and recreate the different kinds of radiation and mix it up and put into some use. So this chapter talks about that in some great detail. This is what, if you could see it, this is what the electromagnetic waves. If we took a magnetic field and an electric field and we combine both of them, they're always orthogonal. They're at 90 degrees to each other, but they're not steady state. They're not stationary. the magnetic field and the electric field, they're always oscillating like this at 90 degrees to each other. And so it's difficult to show. Just using two hands, I need about 6 of them. But the reader can get all of that from this chapter. So the changing magnetic field induces an electric field, and the changing electric field reintroduces, or induces rather, a changing magnetic field, and they go back and forth. And as they're oscillating back and forth in magnitude, they're both rotating always at 90 degrees. And as they're rotating, they are propagating either forwards or back in a direction that's perpendicular to the plane of their oscillation like this. So it's actually quite complicated to show, in such a setting, but the description I've given the chapter should hopefully clear that up. So this is what actually sunlight, visible light, would look like if you could see it. All 7 forms of radiation, electromagnetic radiation, would look like this. A fluctuating electric and magnetic component, orthogonal or 90 degrees to each other, that's rotating and propagating at the same time. In vacuum, it moves at the speed of light. All 7 forms of radiation, they all move at the same speed, the speed of light, which is 300 million meters per second, or 186,000 miles per second. That would wrap around the Earth 7 times if light could bend around corners at that speed in 1 second. So it's quite fast. So once the radiation hits different kinds of media, like atmosphere, Earth, or whatever it is, the speed is no longer the speed of light. It drops to below the speed of light. That's a measure of what's called the refractive index of the material, how it affects light. So this chapter deals with how we can calculate the speed of light, both from Faraday's laws and from Maxwell's laws as well. They both are able to derive the only absolute constant in the universe, which is the speed of light in vacuum. It's quite phenomenal. So the wave depiction, because the electromagnetic waves are just that. They flow sinusoidally. So the representation are shown over here and how we can manipulate the different parameters, like wave number, angular frequency, etc. are dealt with in several examples are handled. We talked about something called the root mean square value, which is really an engineering term, but it's a mathematical tool to facilitate what the maximum value of any component, electric or magnetic, would be at any given time at any given location for a wave. It's actually very, very useful in engineering. So I've shown how all that's calculated. Also talk about the energy that's being transported in a wave. If a material absorbs radiation, material being you or myself, we step outside, we feel the heat from the sun, we're absorbing radiation from the sun in many forms, infrared, ultraviolet, and a few other forms. The energy is carried or determined by something called the pointing vector. And I've derived the pointing vector and how it is used to calculate the intensity of radiation. This intensity of radiation is derived by the pointing vector. It turns out that as radiation is being produced, for example, in the core of our sun, this radiation, this energy is propagating outwards in all directions, and it actually creates pressure on the outer layers of the sun, of our sun, and it's supporting the weight of the outside layers, so gravity doesn't win this battle and cause the sun to collapse. Now, this is only possible, for stars as long as the star is alive. When nuclear fusion is going on in the core. Once the fuel runs out, the nuclear fusion stops, gravity wins, and the sun collapses, either in a very boring, less than ceremonious end, like a white dwarf, or in a fantastic explosion, a supernova explosion, and neutron stars and black holes and stuff can all form. So very interesting things can come out of this. This radiation pressure, it actually holds up stars from a gravitational collapse and lets them, this only exists, of course, while the star is living a useful life. So I've shown the calculation, the derivation, all of this, and I've taken the reader to some of the places that I've been here, from pole to pole. This is Antarctica. It's me on a boat. I was open ocean kayaking with the killer orca whales and stuff. I was on my way to do that in Antarctica, fellow years coasting Antarctica. So I calculated what the electric field component would be at that particular latitude, so far down close, not terribly far from the south pole of the planet in Antarctica. And believe me when I tell you, the most important thing is not a warm jacket, it's sunglasses. because this is where the ozone hole exists. It's over Antarctica, so more ultraviolet radiation enters into the Southern Ocean over Antarctica compared to any place else on Earth. And also with all of the tremendous coverage of the white snow and ice, it reflects ultraviolet radiation, and you'd go snowblind in less than a day. So having really good sunglasses is a must. This is not the time to buy cheap sunglasses for a trip to Antarctica. So just a bit of a tidbit over here. And so I've taken the reader to other places. I've gone from close to the South Pole to close to the equator. This is in Tanzania in Africa. It's a little kid. I think it's a little kid as I drove by in a 4x4 here on the open African safari, the Masai Mara. I was following the wildebeest migration. And the big 5 animals that hunt the wildebeest. So wherever the wildebeest went, I went. So I was calculating what the intensity of the radiation would be, how it would be different if you're close to the equator compared to being in Antarctica, for example, and other places. This is Tanzania in the Serengeti in Africa. This is what happens here. It's a dog-eat-dog world out there in Africa. And everyone's fighting for something, even in Africa. And so I did the calculations for the different magnitudes of the intensity levels of radiation that not just animals, but people as well have to deal with, depending on where you live. And it's not the same. Depending on where you live on Earth, much like animals as well, as I've shown here, people succumb to different levels of radiation. And this has to do with every facet of existence, even the color of one's skin, depending on where your ancestors lived. If you lived in a region that was prone to a lot of ultraviolet radiation throughout the course of the year, nature gave you a significant amount of melanin, and melanin colors your skin brown, as opposed to people whose ancestors lived in a region where there wasn't a whole lot of sunlight for 10 months of the year. Not so much of a worry, so there's no need to use vital calories, organs, and the efficiency of bodily functions to create melanin when you don't need it, because there's not a lot of protection needed, because there's limited amounts of ultraviolet radiation. So even the color of your skin, which is a source of many, conflict today around the world, but that's a separate story. But even that has to do with radiation, how nature tries to counteract it. And this is the other pole. This is close to the North Pole in the far north of Norway, well inside the Arctic Circle, the land of the midnight sun. It's actually about 1 o'clock in the morning there. The sun's very, very bright. So I did some calculations to show what the intensity of radiation would be there as well. So the reader has a lot of information to work with. This is an actual photograph of the solar eclipse that occurred in 2017. Picture was taken in Tennessee. And so I did an example, a calculation of the ratio of the radiation, the force of the radiation pressure from the sun on the Earth compared to the gravitational pull of the sun on the Earth. So it's actually quite an interesting example, because the radiation pressure is pushing the Earth out, and the gravitational force from the sun is pulling the Earth in. Obviously, the one is much, much greater than the other. So I did a calculation here of the force of gravity versus the force of radiation pressure, and it's literally billions of times stronger, the gravitational force, than the radiation pressure. But it's quite a fascinating example. I think the reader will get quite a bit of knowledge from this. And finally, I've talked about the electromagnetic spectrum. I talk about the different entries here: the gamma rays, X-rays, ultraviolet, visible light, which is the colors of the rainbow, infrared, microwave, and radio waves. So the reader should have a really good understanding of the concept of electromagnetic radiation, radiation pressure, the Poynting vector, and how all this is put together through Maxwell's equations. I hope you've found this very enlightening and helpful. Once again, I thank you for your time.